Hello. Yeah, welcome to session number 25 in the series Microwave and Millimeter Wave Circuit Design. I'm Anurag Nigam, and in this session, I have a task at hand to convert this circuit into a layout without affecting much of its performance, right? So that's the whole idea. So its performance is over here. Uh, let's look at the data display window. So its performance is over here, right? And we do not want to affect a lot of any of this stuff. And we should be able to transform this circuit into layout. So most of the engineers, they usually fail at this point, and they take multiple revisions costing a lot to the company, right? So I'm going to show you how to do this, right? Without in how to get the results in maybe one or two turnarounds rather than doing multiple turnarounds, right? So this flow you have to keep in mind. So now one thing is there, this LNA is part of a radio front end chip. So the output of the LNA is going to see bond wires, while the input of the LNA is going to see a switch, right? So the switch is not yet designed. So basically when we transform this layout, I would have to first put bond wires at the output. So to do the bond wires, so two wires which are going to be 1 mil is going to be sufficient to put out the power, right? So what I'm going to do is I am going to simulate those bond wires. So I'm going to go to here, and I have already got the 3D done for the two bond wires, and I'll just show you what that looks like. Okay, so basically that looks like gallium arsenide. So this gray colored thing which you are seeing, that's a gallium arsenide, right? And that is sitting on a pedestal which is going to be your ground. So in a QFN package, usually there are multiple vias, right? And there are lots of vias which are going to connect the bottom ground to the top ground over here, right? And because there are so many vias, I am just going to replace them with one solid piece. This is one solid piece of ground, and on that there is gallium arsenide sitting, and this is basically your alumina, Al2O3, right? And this is usually used in most of the processes to do the QFN. So this is done usually by a HTCC process, right? So that's alumina, and that is sitting, and this terminal is the pin, right? So usually you will see that this is like a QFN, right? But this is a small piece of that QFN, right? So if you want to understand the diagram, I can explain you in terms of uh, what you call a diagram, right? So this is what a QFN is going to be like. And if I just cut a small piece or a section of it, sorry, this is going to be like this from the top view, and this is going to be the side view when I slice it out. So these are the two bond wires which I'm going to see here, right? So that's what it is. And I have simulated it from DC to let's say uh, 40 gigahertz, right? So I'm going to look at S11 and S22, so they are overlapping, and then S21. So at the frequency of interest, this is like 20-25 dB, right? So 20-25 dB is good enough, right? And so if you want to see this, you can also see this in the Smith chart, right? So you can see this in Smith chart. So this is what is happening. So this is what is happening. So these are going to start from 50, and then they are going to turn around like this, like an open circuit. So this is going to go like this into an open circuit, and the other one is also going to go like this into an open circuit. So this is because it is a series inductance, right? And then there is a little bit of capacitance which is doing this to come down, right? But at our frequency of interest, we are somewhere over here, right? So we are good enough. So I'm going to just cancel this. What I can do is I can export this and export this as a touchtone file. So I'm going to export this as a touchtone file to, let's say, my desktop, right? Save it. And then I am going to, because I'm running an older version of ADS, so I have to get it into my virtual machine, right? So what I have to do is, okay, I have to go here and get that bond wire over here. So Where's my mouse? Okay, so what I'm going to do is I am going to go to uh, desktop. So this is not the desktop I'm looking into, right? So I have to go to my computer shared folder and desktop. And here I have placed bondwire.s2p, isn't it? No, this is not the one. So let's go ahead and do the export again. Right click, export touchtone file. This is called bond wires. Sorry. So this should be called bond wires. Sorry, typing mistake. Save. So this is exported as bond wire. So it should show up on my desktop, right? So over here, if I refresh this, okay, I should see bond wire s2p file. So this one I am going to place on this desktop, isn't it? Is it copied? Or I can just copy it, right? Copy, and then I go to C drive and I locate under user. I go to designer and I'm working on 6E. Under data, I will place here paste. So this is called bond wires, not bond wire, bond wires. Okay, so that's cancelled. So the next thing which I'm going to do is I'm going to put that bond wire over here. So I'm going to get rid of this and I'm going to put here a data component, right? So I'm going to put here a data component which is a 2-port S parameter file. Okay, and here I am going to read that file. So I'll browse for it. It's called bond wires. Open it and it's a touchtone file, right? So this is done and I have to give a ground reference and all I have to do is connect this. So now this is with the bond wire. So let's see the effect of bond wire. So if I simulate this, okay, so the match has changed slightly in the sense that it has moved, right? So I am going to simulate in our band and try to adjust it. So I'll go here and adjust. So I will go from, let's say, 5.95 gigahertz to 7.15 gigahertz. So I want to adjust it in our band in steps of 10 megahertz. Say OK, and I hit this simulate again, or rather I can hit tune. Okay, so once I hit the tune, this is what I have to focus on. This has to improve, right? So if I look at the output match, okay, so the output has moved. So C6, okay, so these are the ones which are going to affect it, right? So I'm going to adjust back our match to where it was, right? So you have to have a good mouse control. And I want the return loss better than 10, right? So I don't want to go across 4 picofarad. So this is 4 is the best I can go. And this one, so I don't want to do that. And this one is going to adjust it down, and this inductance is going to take it up, isn't it? Uh, okay. Okay. So we are getting back to where we were, right? So either you can focus on Smith chart, or you can focus on your rectangular plot, right? You can focus on either of them to position this. So really, I want a good match here. So I want a good match over here, right? And let's see what I can do with this. So if I want to make it 1.6, right? And uh, so okay, 4.2 picofarad. This is going to be a really lossy cap, okay, which I hate. And this one is affecting your nice figure, right? So this one is affecting your input match, so you are mismatching it, correct? And this one is gain, and this one is directly hurting you on the noise figure. But this is what I will, so I don't want to lose the gain in the noise figure just for the return loss, right? So let's see every one of them. So this one is interstage matching, is it? L1, this is input match, correct? And so this is better than 10, and this is also input match. This one so supply I don't want to hit, and this one is affecting your, and over here okay, so I'm gonna accept this match, right? It really depends on, you can keep doing this, but I'm gonna stop here. And what have I done? Okay, I have a return loss, but still I'm shy of return loss here, which I don't like, right? So I'm shy of return loss there. So these things are going to be adjusted number of times. So really this is not the point where you're going to really worry about this a lot. So really this is your capacitor, and this one fine, and this capacitor is, let's say, 4.2. Okay, 4.2, and let's see, we are better than 10 here, right? We are better than 10 here. So I'm going to update this and I'm going to close it. Okay, so what do I have for performance? I have nice figure which is going to be 1.8 going down to 1.78 to 1.8, so it's almost flat. Gain is going from 20 point something to 19.4, right? And in between it is going to be something here. So that is gain variation, right? And noise figure is over here, return loss is over here. Okay, so I'm going to stop here for the tuning part. So what did we do? We basically got a bond wire included in our design. Now the idea is to transform this into a layout. So I'm going to do section by section. Section 1, I'm going to have this one transformed, the CLC transformed into a layout, right? So I'm going to record this in parts. So part 1, which will follow this, I'm going to transform this into layout. So I'm going to stop here, and then in part 1 I'm going to do this. Okay. Okay, so here we are with a two-stage LNA, a cascode LNA, and we have included a bond wire here. And now what we have to do is, first logical step I see is this via has to be, right now it is a two-part. One is the via inductance which we simulated in momentum, and then we introduce the additional inductance here of 90 picohenry, and that has to be absorbed into the layout. So what we do is we just copy this section into a separate file and find out what this inductance looks like. So what I have done is I have copied this over here, and then I'm going to do a single port S parameter simulation in my band of interest. So once I do that, then what I have to do is I have to replace this circuit inductance with a trace of line in the layout. So the layout originally is this. Now I would modify that to include a certain inductance over here. Now you have to note that this is the source of the device, and source has to carry the entire current. So whatever trace of line which you introduced in between here, it has to be wide enough to carry the entire source current. So what I have done is I have taken a 10 micron wide line, and then I have modified the layout to look something like this, right? So in this case what I have done is I have moved these two vias apart and introduced a trace of line here, like a meander line on both sides into the layout, and I do the EM simulation in my band of interest, right? So once I do that, then what do I have? Let me see. Okay, so once I do that, I can compare the circuit simulation with the response from the EM simulation, and this looks like this. So the red one is basically this EM plus 90 picohenry circuit, while the blue one is the 90 picohenry has been absorbed as these two meander lines, right? So once I do that, they are almost there. Now why this is important is because this inductance decides both the interstage impedance as well as the input impedance. So as to have that same as in the circuit, I have to match these two. So once I do that, then I can go ahead and run the simulation from 0 to 40. So 0 to 40 what you call 0 to 40 gigahertz, and then I can make a lookalike. Like over here, I can make a lookalike, and then I can introduce that lookalike in my circuit and resimulate the circuit. Now if that requires retuning these components, that I will do. So in this part I am just going to replace this source inductance with the lookalike from the layout. Okay, thanks, see you in the next part. Okay, so now I'm done with the simulation here, and I'm going to do a replace this combination here. This combination here I'm going to delete, and then I'm going to replace it with a lookalike for this component, right? So I'll go to the main window, right, and from the main window I am going to just drag the lookalike. So this is called via2, so that's the lookalike for that, and I'm going to connect this over here. So this is a lookalike for that via with the additional inductance here, right? So that I have included in the layout EM simulations. So now I want to see whether my performance has moved. So I'll just simulate this, and once I simulate I see that it hasn't moved, right? So basically we are on the right track. So now what is the next step? The next step is I'm going to translate this one by one into a form which is going to give me the same impedance as the input. So I'm going to copy this, and I'm going to copy this into a new schematic. So that is the input match. So I'm going to copy this into a new schematic. So let's make a new schematic, and I'm going to paste this here. Edit, paste. So the idea is to proceed to the input of the transistor, right, from a 50 ohm, right, and keep on matching impedance. So first I'll realize this capacitor, a series capacitor, and then this combination, and then I will do this combination, and then I will do this combination, and make sure that my impedance looks the same in EM simulation as well as the circuit simulation. So what I'm going to do is I'm going to save this as file save as, or rather I'm going to make a new layout. Okay, so in the new layout I need a capacitance. So let's see how much capacitance do I need. Okay, so I need a capacitance which is going to be 2.866 picofarad series capacitance, right? So I am going to go here to my library and look for a capacitor. Now this capacitance, okay, is 1 picofarad here, and it maintains it to be a square, right? So I want 2.866, correct? Say apply. So now here I can make it a square, because what happens is if you make it a rectangle, then the current densities on the corners are going to be much high. So it's better to make it a square, right? So here let's say I'm going to do 50, so that's 89. So let's say if I do 60, that's going to be 72. Let's say 65, that's going to be 67. Okay, so 66 would result in 67. Let's say 66.8. Okay, so this is almost a square, right? So I'm going to use this capacitor, right? I'm going to use this capacitor as a series capacitor, and I want to make sure that the EM simulation of this series capacitor at my desired frequency of interest gives me 2.866, right? So then after that I'm going to create a shunt inductor and then put them together, right? So I'm going to break this part again and EM simulate this part. Okay, great, thanks. Okay, so this is the LNA, and in LNA the most important parameter is the noise figure, and the noise figure is referred to the input, and the noise figure is dominantly affected by the noise figure of this transistor and the loss of this input match. So when I implement LNA, I have to proceed from input to output, right? So I would copy this portion, which is the input match, onto a separate schematic over here, right? And here I would go component by component matching the impedances. So first I will establish this capacitor, and this capacitor is basically this capacitor over here, and then this shunt inductor, which is basically this shunt inductor with the via to the ground, and then there is a series capacitor over here, and then finally a shunt inductor which is bypassed by these caps, right? And there is another port over here. So this is a 3-port network here, another port which is terminated into 50 here, and it is terminated into 50 over here in layout. So the layout basically looks like this. Now how do I proceed designing this? I go component by component. So if you focus here, okay, so I go from 50 ohm, which is over here, 50 ohm. I go over here from 50 ohm through a capacitor to over here, and the red one here is the circuit component over here, and the blue one is the EM simulation from here, right? So that's the one. So after that, so I have reached here in the circuit as well as the layout. Then I use a shunt capacitor, shunt inductor to proceed up to here. And again, the red one is the circuit simulation, and the blue one is the EM simulation. So I have included this inductor in this simulation here. So I have a series cap and a shunt inductor. So I have reached over here. Similarly, in the layout, I have a series cap and a shunt inductor over here, right? So this shunt inductor goes to ground. So I'm over here. After that, I have a series cap which is over here. So this is my series cap, and similarly there is a series cap over here. Sorry, this is the series cap over here, this series cap, and that would bring me up to here. So in this case, I am over here. The blue one is the EM simulation, and the red one is the circuit simulation. Then a shunt inductor will take me over here, right? So that shunt inductor is basically this with this bypass caps. So that has taken me over here. Similarly, that shunt inductor in the layout is over here through this bypass cap to ground, right? So that has brought me up to here. The red one is the circuit simulation, and the blue one is the EM simulation, right? So notice here, when I proceed from input side up to the transistor, I keep an eye on S21, right? So basically, you see, at everywhere I will keep an eye on S21 and maintain S21 within 2 to 5 degrees. So when I reach finally up to here, I have the phase, S21 phase, differing across the frequency. At high frequency, this is around 1 degree variation, like between EM and circuit, while at low frequency it is a large variation of around 8 degrees. Now this large variation of 8 degrees I'm not bothered about. Why? Because if you notice, in my EM I have a 50 ohm termination over here. In circuit also I have a 50 ohm termination here, but this DC supply establishes a perfect short. So basically this capacitor is basically shorted out with this DC supply, right? In that case, at low frequencies there is an insufficient bypass, while at high frequencies there is sufficient bypass by the caps. So what I'm expecting is, once you put the DC supply here, at low frequency also this bypass would be good. So I'm assuming that after I put a supply here with DC supply, then this 8 degree phase will shrink to 1 degree as over at here at high frequency. So that basically completes my layout. Next, what I'm going to do is I'm going to run this simulation for up to third harmonics. So basically I will go here and run this simulation from DC. DC point has to be included because the DC circuit is solved separately in simulations. And then I'm going to simulate up to third harmonics here, right? And then I'm going to just say simulate. So once the simulation is over, I'm going to generate a lookalike of this and go ahead and place that lookalike in my circuit simulation over here. And once I have done that, the performance will slightly move, and then I would use the other components to get back my performance. So I will proceed from input to output in the same fashion. After that, I'm going to do an interstage match. And once the interstage is done, then I will proceed to the output. So this is done. The layout is generated component by component, making sure that the impedances are matched at every point. And what is important is the phase of S21, which you have to maintain between 2 and 5 degrees, so that the layout is going to be as good as the circuit in performance. So what I'm going to do is I'm going to put this on pause because this simulation is going to be lengthy, right? And then once this simulation is done, I will come back to you, right? Thanks a lot. Thank you. Okay, so once I'm done with the simulation, of the input stage, which is over here as a lookalike. So I have done a lookalike component which represents the layout, and this is my input port. This is where I put in the DC supply, and this is my transistor, right? So I have transformed the input side of this transistor into a layout. Okay, and then I have also refined according to the layout. I have also refined the VI inductance for this transistor, and after that I have tweaked these components to get the performance as it was. And the thing you would notice here is that we were sitting at a noise figure of 1.85, and then suddenly it has shot up to 3.2 as a worst case, right? So now it seems like this noise figure and NF min been differing a lot, right? Then there was a scope of improvement on the transistors and matching. But here NF-min and NF2 are almost the same, right? So then the contribution to noise figure is mostly coming from the loss in the input stage. It is not with the biasing or the tuning, right? Because NF-min and NF2 noise figure is the same, right? So the scope of improvement is not anywhere else other than if you can minimize the loss of this input stage, right? And to do the loss, minimize the loss of the input stage, you can reduce the loss in these inductors, because these capacitors, this path, RF path is so short. Then the loss is not because of these capacitors mostly. The loss is coming from the shunt inductors. So the only thing you can do here is you can make this wider trace on these inductors and try to get the noise figure to go down by reducing the loss. Now, how much improvement can you do on the loss, right? Well, it seems like this is a 1.3 dB loss. And if you can bring it down by, like, say 0.4 dB, your noise figure will go down by 0.4 dB. So basically all the struggle over here for a designer is going to be minimizing the loss of the input stage. But here I am not going to optimize that, because I know that this is a very lengthy process. So rather I will proceed with the flow. And the next thing I'm going to do is I'm going to transform this interstage into the same form of layout as over here, making sure that the matching holds between input and output. So that's the next thing which I'm going to do. Okay, so I'm going to put this on pause again while I'll do this, right? Okay. Okay, so at this point, the interstage is a L, a C, and an L. Now this L is so small that this is just a piece of line from one transistor to another one. That's a piece of line, and then there is a shunt capacitor over here, and then there is a series inductor going to another transistor over here, and then there is a C which is used as a bypass on the gate of the common gate, right? So this results in a simulation. EM simulation results, they look like this. Now in this case, the red one is the circuit element. So there is a first inductor which basically doesn't move you much, so I haven't simulated that separately. Then there is a shunt capacitor which moves you down up to here. So the red one is the circuit simulation and the blue one is the EM simulation at this point. And then beyond this there is an inductor which takes you up this way. So this inductor basically takes you up that way. And again here the red one is the circuit simulation and the blue one is the EM simulation. And then there is this bypass cap which is over here as a short. So I'm going to use this, I'm going to simulate this from 0 to 40, right? And then make a lookalike and use it in our simulation. So this will be from 0 to 40, right? Okay, so I'm going to put you on the pause again and then just simulate this. Okay, so once I'm done with this interstage simulation, right? Once I'm done with this interstage simulation, I put together the input match, the transistor, the the interstage, and then the next transistor, right? So the layout has progressed from input to output, and in schematic, this looks like this. There's an input match, there's an interstage match, and then the only thing remains is to convert the output match. In terms of performance, we are almost where we were. The noise figure is around 3.2, right? And the match is better than 10 dB on input and output. The gain varies from 18 to 20.5, so there's a 2.5 dB variation in gain. Okay, so now what I'm going to do is I'm going to proceed from the output side towards the input side of this final stage, right? And transform all this into a layout. Okay, thanks a lot. Hello. Yeah, uh, in this two-stage LNA, okay, on the input stage, I was suspecting that the impedance was messed up by this node. And if I go back, if you remember, right, I mentioned that uh, that in my simulation, the impedance of the supply, okay, is going to affect the impedance of that the transistor sees, right? And that was not included in the EM simulation. So if you consider here, uh, let me just show you. Okay, if you consider here, okay, here what we had over here, okay, was a 50 ohm termination, but we connected DC supply here, right? DC supply is a AC short. Now if I go here in my simulation results, which is I think this one, right? um, Not here. Let me just open that. Okay, it's over here. Okay, the impedance at this point, right? The impedance at this point, which is the final point, was established because of the shunt here. And if I was to move this out, right, and then simulate it, then this point moves. Now this was the condition in which the method of moment or EM simulation was carried out, and I assume that this capacitor implemented a perfect shot so that this impedance is not going to affect. Now what's happening is that is affecting. So what I am proposing to do is I'm going to insert a resistance here for decoupling. Okay, and resistance can be inserted in the gate bias because the gate doesn't draw any current, right? So that decoupling would be, let's say, 1K. So no matter what is the internal impedance of this DC supply, 1K would be so high that it would be, you cannot do this in the drain supply because drain draws current, but in gate supply you can do that. So 1K will be so large that the internal impedance of the supply won't matter. So this small trick which you can do on the gate side cannot do on the drain side because the drain draws the current. So we have to be careful on the other side in implementation. So let's just put here 800 ohm or 1k ohm resistor and see what happens to the noise figure. So the match, basically the issue here, the noise figure degraded because of the match was not correct here because of this impedance. And so I inserted 800 kilo ohm or 800 ohm resistor near to 1 kilo ohm, and then I do the simulation. So once I do this simulation, I find out that my noise figure is now between 2.4 to 2.3. So this is kind of acceptable. It was 1.85 and it become 2.5. So this is kind of acceptable, right? So this is the small remedy which I have done here, and now I am going to transform the output stage into the layout, and I have to be really careful about what I do over here because this impedance is important, right? So this has to be a very good shot here, otherwise there would be a issue of the internal impedance of this supply, right? So that's all I wanted to tell you. Yeah, so notice how I have replaced each and every match in the layout, okay, into a layout, right? Each and every match in the circuit I have changed to layout. So there is an input match, there is a VI inductance, there is an interstage match, there is an output match, there is a decoupling here, right? Notice this, and also notice that the noise figure is where it was, right? It's around 0.7 dB degraded from the circuit, but that's the best I could get. And if you do few iterations with interstage and the input match, you might be able to drop it further. And if you do some iterations, you may able to keep the gain above 18. Right now the gain is between 15, 17 and 15, right? So if you see, the gain is between 15, 17 and then again 15. So so there is a 2 dB gain variation across the band. The return loss is better than 10 for both input and output, right? And you can see here in S parameters it looks the same as, somewhere in between we had the same thing uh, with the circuit and EM simulation. And this is the nice figure. Now, one thing I want to highlight here is this. Mostly what happens is people do this layout and then they say, okay, the biasing conditions change. So for example, here this DC is a short, right? Now this decoupling has been implemented so that the effect of the internal impedance of the battery is not there, or the DC supply is not there. So let's say, for example, in this situation I change this with a, so right now it is a DC short, sorry, right now it is a AC short here, right? Now if I replace this by a AC open, which a DC feed does, then the performance should not change a lot, right? So that way you are insensitive to what you connect for a DC supply, right? So if I simulate this, I see that my performance doesn't change much. It's just that the gain has also gone up, right? Gain has gone up some places, right, by a few points. But other than that, you see that the performance doesn't change a lot. If I change the internal impedance of a battery from short to almost open, the impedance matching doesn't change. So this is something which people usually do not take care, and later when the chip comes back and they connect the DC supply, the performance keeps changing. Same thing on the gate bias. Okay, so if I was to connect here a open circuit, which would be a DC feed, then the impedance matching should not change a lot, right? If it changes a lot, then there is a problem, right? So if again you see here, it didn't change a lot, right? I resimulated it. So that's the thing which a circuit designer has to make sure. Okay, so having said that, let's put it back to where it was, okay, as a short, right? Okay, so now the entire course simulation, so these are the circuit elements which I removed out, right? So the entire circuit has been changed into a layout lookalike, except the transistors, the DC supplies, the terminations, and the bond wire, right? And in layout form, this would look like this, right? There's an input stage which matches over here. That's your input stage. So if you see here, that's your input stage here and here. That's your interstage over here and here. And that's your output match, so that's your output match, and that's your bias decoupling, so that's your bias decoupling. So that way I have covered the entire layout and layout EM cosim. Right now, if you want, you can go ahead and do a single cosim, but then it depends on your machine, and this is very time consuming, right? So it took me 3 days to reach at this point, right? So you can understand that I'm using a very high-end machine to do this, and if you are using a simple laptop or something, then you will take days to reach here with EM cosim results like this, right? So I conclude here the 25th session, which was very large and it has been done in parts. So bear with me that the audio may go up and down during this session. Thanks a lot. Thank you.